Hello all, in this video we are going to discuss about various types of data fallacies, otherwise called as statistical fallacies. Data fallacies or statistical fallacies are the common tricks that data can play on you, which lead to mistakes in the data interpretation and analysis. In this video, we are going to expose ourselves to some of the common fallacies with real-time examples and find out the ways how we can avoid those data fallacies in our setups. Now, what do you mean by data fallacies or statistical fallacies? By definition, these are the deceptive arguments from the flawed data or analysis. Here, the fallacy may be due to the data collection itself, or during the analysis, we may land up in data fallacies. Now, what are all its causes? The causes for this data fallacies are the biases which occurs during the data collection and analysis, incomplete data or inaccurate data, the misinterpretation of the data or the results, and manipulation of the data or analysis. All can lead to data fallacy or statistical fallacy. Again, this data fallacy may be intentional or accidental. Now, what are all the consequences of data fallacies? Mostly, it leads to misleading marketing of items, persons, etc. etc. It can produce a biased research. It can make faulty policies out of the existing data and its analysis. Now, first data fallacy is the confusion between correlation and causation. People say association and causation in epidemiological studies. This fallacy occurs when two variables are correlated or associated or moved together. Then people assume that one is the cause of the other. That is, presence of two factors more than its expected chance. Instead of assuming it as associated variables, we assume that one factor is the causative factor for other. Here is one example where ice cream sales and sunburns both increase in summer. One does not necessarily cause the other, but there is a third variable called the warmer summer could be influencing both. So in this case, people think that the sale of ice cream or the consumption of the ice cream and the incidence of the sunburn both will be higher during the summer time. Actually, this is a correlation or association. One cannot assume that ice cream is the causation for sunburn. Actually, these two variables are connected to a common variable called the sun that causes the dry weather. So people eat more ice creams and the same factor causes more sunburns. So there is a third factor which might be a cause, and these both are associated factors or correlated factors. So people often confuse between causation and correlation. So often correlations between two things tempt us to believe that one caused the other. However, it is often a coincidence or there is a third factor causing both effects that you are seeing. Now, how can we get a clear picture between an association and causation? We have a Bradford's Hills criteria for that in epidemiology. So we can use those criteria and differentiate between association and causation or correlation and causation. So Bradford's Hills criteria can be used. Bradford Hill has given different set of criteria and he has mentioned how smoking has become the causative factor for lung cancer rather than being an associated factor. Next, we move on to the interesting data fallacy, that is cherry picking. Cherry picking is otherwise called as selective attention. It refers to the practice of showcasing only the information that supports a specific conclusion while disregarding any evidence that contradicts it. This represents one of the most severe damaging forms of dishonesty with the data. So here is the example. From the same data, people can take out a particular trend and he can say that the unemployment is high. On the other hand, the same person can take out a segment of the data and can say the unemployment is down. So mostly politicians usually cherry pick the data. They take whatever they want, use it for their purpose. Instead of looking the data and information at a larger context or the overall context, they take out the segment and speak about the bad effects or good effects of that particular time period. So individuals often emphasize data that reinforce their argument instead of considering the complete set of results. This behavior is common in public discussions, especially in TV discussions and politics, where opposing parties can each present statistics that favor their own viewpoint. Cherry picking can occur either intentionally or unintentionally. For instance, a company might spotlight a time frame with elevated conversion rates while neglecting to disclose data that indicates a general decline in website traffic. If they intentionally miss out certain key factors and they take only one segment or one area of information, then that phenomenon of data fallacy is called as cherry picking or selective attention. The next data fallacy on our list is survivorship bias. It is drawing conclusions from an incomplete set of data because that data has only survivors based on some selection criteria. During the World War II time, a team was asked to identify what is the best place to fit armor to a plane so that that armor can protect the plane. So the team assessed the planes that came back from the battle and had bullet holes everywhere except the engine and the cockpit. These two are the most vital areas of the flight. When the flights were not hit at that area, the flights returned. The team decided it was best to fit armor where there were no bullet holes because planes shot in those areas had not returned. So the survivorship bias in real life scenario occurs while studying successful entrepreneurs. We conclude that certain traits are necessary for success without considering the many others with those traits who have failed. And if you suppose we want to train a person, we also should read failures, not only the success. Next on our list is sampling bias. Sampling bias is drawing conclusion from a set of data that isn't representative of the population that you are trying to understand. Sampling is a process by which we select the sample from the study population. If the sample is not truly representative of the study population, then the study results from the sample cannot represent the study population. So here in this example, if we are conducting a survey about internet usage among the people who have smartphones, so we have a sample where internet usage is going to be very high. So they report that internet usage is going to be high. So we have a sampling bias. So we may land up in sampling bias resulting in overestimation of the internet usage among the people. So it will not be a true representative of the population which we intend to study. Next on our list is the gambler's fallacy. Gambler's fallacy is a phenomenon where people mistakenly believe that because something has happened more frequently than usual, it's now less likely to happen in future, and vice versa. Suppose if we are tossing a coin, if head comes now, then usually the human tendency will believe tail is going to come next. But actually the probability of head and tail at that point of time, it is going to be equal for head and tail. But if head happens the previous time, the tendency of the mind will believe that next is going to be the opposite. So that is called as gambler's fallacy. It is also known as Monte Carlo fallacy because of an infamous example that occurred at a roulette table in 1913. The ball fell in black 26 times in a row and the gamblers lost millions betting against black, thinking that black has occurred previously, so next time black will not happen. The chance of black is always same as the red regardless of what happened in the past. That is true, so the probability is going to be the same before rolling the ball, because the underlying probability is always unchanged. It is going to be the same for both black and red every time. Usually people think that after a coin has landed on heads multiple times in a row, it's due to land on tails. So we think that way. As I told, every time the coin is tossed, the chance of head and tail is going to be equal. There is no connection between the past results. So if our mind is biased with the previous result, that is called as gambler's fallacy. Next on the list is the data drenching. It is repeatedly testing a new hypothesis against the same set of data, failing to acknowledge that most correlations were due to the results of chance. Data dredging is otherwise called as p-hacking. It is the fallacy of performing many statistical tests on a data set without a predefined hypothesis and then highlighting only the statistically significant results which may have occurred by chance. Our objective would have been studying something, but we need significant results. So we will be testing multiple hypotheses to get statistically significant results. Historically, this has been a problem with clinical trials where researchers have data dredged their results and switched what they were testing for. It explains why so many results published in scientific journals subsequently being proven to be wrong. To avoid this, it is now becoming standard practice to register clinical trials stating their hypothesis or the primary endpoint measure in advance. So if we do that, this data dredging issue will be minimized. Next on the list is regression towards the mean. This is a fallacy. When something happens that's unusually good or bad, that is on the extreme values, it will revert back towards the average over time. In other words, it is failure to recognize the extremely high or low values are likely to be followed by values closer to the average. Here is one more example for this. A sports team having an exceptionally good performance in a season might be expected to perform less exceptionally in the following season, not necessarily due to a decline in the skill, but due to statistical regression. If a sports team has performed very good in the previous season, the next season our normal expectation will be towards the average, not towards the same performance in the past. So this fallacy is called as regression towards the mean. Next on the list and the most important fallacy, that is Simpson's paradox. It happens when a trend appears in a different subsets of the data but disappears or reverses when the groups are combined. I will come to this example after explaining this. Simpson paradox is a phenomenon in which the trend appears in different groups of data but disappears or reverses when the groups are combined. This classical example happened in the 1970s, where Berkeley University was accused of sexism because female participants were less likely to be accepted more than the male ones. However, when trying to identify the source of the problem, they found that individual subjects, the acceptance rate were generally better for women than men. The paradox caused by a difference in what subjects men and women were applying for. A greater proportion of female applicants were applying to highly competitive subjects where acceptance rates were much lower for both the genders. So here is the gender-based accusation of sexism towards that university was given based on this results only. Out of the male, in total 28% were selected, and out of the female, only 19% were selected. So here people believe that male applicants were more preferred than the female applicants. But when we look at the individual subjects, females have applied for more difficult subjects. That is, the subject 1 overall rejection rate is high. 14% of the male and 15% of the females were selected here. And in subject 2, the selection rate was high. 50% of the males and 51% of the females were selected. So hence there is no difference in selection. Simpson's paradox has occurred because more female have applied for the difficult subject. So this tendency of a trend appearing with a subset or a group but disappears or reverses within the subgroups, it is called as Simpson's paradox. Now this is different from ecological fallacy, where Simpson's paradox is between group and subgroups. Ecological fallacy is between groups and individuals. So this is ecological fallacy, which occurs when somebody draws conclusion about individuals based solely on the group level data. In this example, people falsely assume that every individual's IQ is high in this class, since the class average IQ is high. When we take the average of the IQ, it will be above 100. So people think that the average IQ of this group is high, so all will have high IQ. But there will be one person who have a low IQ, so the group level data cannot reflect the individual level data. So this fallacy is called as ecological fallacy. In 1950, Robinson coined the term ecological fallacy. He referred to the error or interpreting variations in environmental settings as variations among individuals. Now you need to remember the difference between Simpson's paradox and ecological fallacy. Ecological fallacy is between group and individual. Simpson's paradox is between group and subgroups. Next on the list is McNamara fallacy. When people rely solely on the metrics in complex situations and losing sight of the bigger picture, then that is called as McNamara's fallacy. It is otherwise called as quantification bias. People will look more into numbers and quantitative analysis, and because of that it is otherwise called as quantification bias. It happens when we make decision solely based on the quantitative metrics while ignoring qualitative factors or aspects that are difficult to measure. So when we understand such factors, we have to rely on those factors and take decision based on that. We should not only restrict our mind to numbers alone. So when this happens, it is called as McNamara's fallacy. The name McNamara fallacy has come from Robert McNamara. He was a US Secretary of Defense who believed truth could be only found in data and statistical rigor, that is in numbers alone. So the fallacy refers to approach of taking enemy body count as the measure of success in the Vietnam War. So he believed only the success of the Vietnam War will be from the count of the enemy's body only. He was obsessed over those numbers and missed out many relevant insights like the shifting mood of the US public and feelings of the Vietnamese people. He ignored all such factors and he analyzed only the body count of the enemies. So when we are analyzing a complex phenomena, we are often forced to use a matrix as a proxy for success. However, dogmatically optimizing for this number and ignoring all other information is risky. And the fallacy which occurs due to the ignorance of all other factors and relying only on the numbers is called as McNamara fallacy. Next on the list is false causality or post hoc ergo propter hoc, which is one of the interesting and most favorite fallacy which Indians have. I will explain what it is, then I will tell the Indian examples. It is called as post hoc ergo propter hoc. Is a Latin phrase which means after this, therefore because of this. That is, when something happens after an event, people believe that that event has caused this event. This is after this and therefore because of this. It describes the logical fallacy of assuming that because one event follows another, the first event caused the second. For example, if a mirror breaks and then someone experiences bad luck, it's a fallacy to assume that broken mirror always caused the bad luck. So here in this example, the person has crossed a red light, he got headache. He believes every time he crosses red light, he develops headache. So this phenomenon of attributing an event or predicting an event based on the previous event. People believe that when cat goes before an important thing, the outcome is going to be negative. So these are all some of the examples where Indians firmly believe in this false causality. That is post hoc ergo propter hoc. Next on the list is Cobra effect. Historically it is connected to Indians. This effect occurs when we set up incentive that accidentally produces the opposite result rather than the intended result. So that sort of incentive driven negative effect is called as Cobra effect. It is also called as perverse incentive. It occurs when intended solution to a problem. It may be either incentive or some other manner where we want to produce a desired result, but the result has gone in the opposite way. We suggest a solution to a problem. That solution inadvertently makes the problem worse due to the unintended incentives. It is said that in 19th century, the British Empire wanted to get rid of cobras. They want to reduce the cobra bite deaths in India. They offered a financial incentive for every cobra skin brought to them to motivate cobra hunting. But instead of people killing the cobra, people began farming of the cobra. Then when the government realized that the incentive wasn't working, then the cobra farmers released their snakes, increasing the population of the cobras. So this method of addressing a problem with a solution has worked in a negative way. So this is called as perverse incentive or Cobra effect. When setting an incentives or goals, we have to make sure that we are not accidentally encouraging the wrong behavior. So for this Cobra effect, there is one more example in Vietnam where the government want to get rid out of rat. The government gave incentive when people cut down the tail and give to the government. Then people started realizing that once the rat population goes down, we cannot get the money. So what they did is they cut only the rat tail and they gave it to the government, and the rat multiplied. When the government realized that the rat population were not coming down, in fact it has increased the rat population, then they closed this incentive for the tail of the rat. So this is also an example for Cobra effect. Next on the list is Hawthorne effect. Here the act of monitoring someone can affect the behavior. That is, if somebody feels that they are monitored by somebody, their behavior will change. This leads to curious findings. This is also called as observer effect. So Hawthorne effect occurs when the act of monitoring by someone can affect the person's behavior. In 1920s, Hawthorne Works, which is an Illinois factory, did a social science experiment, hypothesized that workers would become more productive following various changes to their environment, such as they tried working hours, increased lighting levels, and break times. However, it turned out that what actually motivated the workers' productivity was someone taking an interest in them. That is, because of increased lighting, people thought that they were monitored by their supervisors, their productivity increased. So the act of the change in behavior by people when they feel that they are seen by somebody or monitored by somebody, that effect is called as Hawthorne effect. Next on the list is gerrymandering. It is manipulating the geographical boundaries which are used to group the data in order to change the results. So the practice of deliberately manipulating boundaries of political districts in order to sway the result of an election, it is called as gerrymandering. Next important fallacy is overfitting. That is creating a model that's overtly tailored to the data that you have and not representative of the general trend. That is, when we are looking at the data, we want to understand what the underlying relationships are. To do this, we create a model that describes them mathematically. The problem is that more complex the model will fit your initial data better than the simple one. However, they tend to be very brittle. They work well for the data you already have, but they find very hard to explain the random variations. Therefore, as soon as you add more data, they will break down the model. So hence simpler models are usually more robust and better at predicting future trends. So here in this example, this will be the right fit or the mathematical model. It is just right, but when we try to incorporate more complex models, so the model will break down. This phenomenon is called as overfitting. Next on the list is the publication bias. Interesting research findings are more likely to be published, which will distort our impression of the reality. So hence we will not get the picture of the reality. For every study that shows statistically significant results, there may have been many similar tests that were inconclusive. Most of the no associations will not get published. However, significant results are more interesting to read about and are therefore more likely to get published. So this sort of publishing only statistically significant results will result in publication bias. Not knowing how many boring studies were filled away impacts our ability to judge the validity of the results we read about. When a company claims a certain activity had a major positive impact on growth, other companies may have tried the same thing without success, so they don't talk about it. So this is in economic setting. This happens due to publication bias. Next, we move on to the danger of summary metrics. Only looking at the summary metrics and missing the big differences in the raw data will result in data fallacy. Danger of summary metrics. The statistician Francis Anscombe put together 4 example data sets in 1970s. It was known as Anscombe's quadrant. So this one, each data set has same mean, variance and correlation. However, when graphed, it clearly indicates that each of the data sets are totally different. The point that Anscombe wanted to make is that the shape of the data is also important as the summary metrics and cannot be ignored in the analysis. We need to have the summary and also the visualization. Both needs to be done in statistics in order to avoid data fallacies. That is also misleading visualization. So using graphs or charts that distort the truth. Example, axis manipulation can lead to misleading interpretations, and misleading scales also can cause misleading visualization. Most commonly, a bar chart that starts the y-axis at 90 instead of 0 to exaggerate the differences. That is, let's say if the BP difference is 90 and 100, this is 90, this is 90 and this is 100. Instead of making this type of graphs, they start the graph from 80 and show it as 90, this as 90 and this double the time as 100. So which means the graph is starting from 80. So this is 10, this is 20. So totally it makes up to 100. So this sort of misleading visualization and danger of summary metrics has to be considered as data fallacy. Finally, to summarize about data fallacy or statistical fallacies are the common tricks that data can play on us, which can lead to mistakes in the data interpretation and analysis. If we are aware of this common data fallacies or statistical fallacies, being aware of this data fallacies or statistical fallacies is the first step to avoid those fallacies. We need to have a critical thinking sound statistical methods, unbiased, transparent approach to data analysis are all essential to ensure the validity or accuracy and reliability of the data-driven insights. To end up, data has lots of power, numbers have lots of power, and it should not be misled intentionally or unintentionally. We should not land ourselves in this sort of data fallacies or statistical fallacies. Hope you found this video very useful. Please share it to your friends. Thanks for watching. If you like this video, please click on the like button. If you haven't subscribed to the channel, please subscribe. Thanks again for watching.